Hello students, welcome to the channel. So in today's video, we are going to discuss the very important concept of vapor pressure. Now, what I have felt during all these years of teaching is that a lot of students don't understand or don't appreciate, rather, let's say, the subtle difference between vapor pressure and any other normal pressure of a gas. And guys, let me tell you this, that vapor pressure or gas का pressure एक normal pressure of gas इन दोनों में बहुत difference होता है. These two are very different things. And the purpose of this video is to highlight this difference. Okay. So what is the vapor pressure? Let's quickly run through the definition, and then I'll be taking some very good examples to make you understand that what is the fundamental difference between a normal pressure of a gas and the vapor pressure. So let's read the definition first. The partial pressure exerted by liquid vapors, when there is liquid gas dynamic equilibrium is called the vapor pressure of liquid. So basically, let us say that we have a container, and in this container, we have taken some liquid. For example, let's say water. So I have H2O liquid. Now, this water liquid will have the tendency to evaporate. It will form the vapors. That evaporation will obviously happen from the surface. Okay. And basically, I am talking about this process. H2O liquid goes to H2O gas, which, my dear students, is known as evaporation. Now, as the vapors will form, the backward process of condensation can also happen. I hope you know all of this. Okay. Backward process of condensation can also happen. And eventually, after a certain time, both these processes of evaporation and condensation will start happening at the same rate. So once the rates of both these processes, that means to say that rate of evaporation is equals to the rate of condensation. So once both these processes have started happening at the same rate, then at that point of time, the pressure of these vapors, okay, when they have reached the equilibrium, at that point of time, the pressure of these vapors of the liquid will be known as the vapor pressure. Because see, once the rate of evaporation and condensation have become equal, then the amount of vapors will also become constant over here. Okay, I mean, as many molecules are going into the vapor phase, the same number of molecules are coming down into the liquid phase. So amount of vapor over here, that will become constant. And that pressure, guys, will be known as the vapor pressure. And suppose you have connected a small device over here to measure the pressure. PMD stands for pressure measuring device. So what will you notice in this device is that the pressure was initially rising because more and more vapor was forming. But gradually what will happen? It will reach a constant value, and after that, it will become constant with respect to time. So that constant pressure, guys, is known as the vapor pressure. Okay, so this is the basic definition which you will find in most of the textbooks. But what many students fail to understand is that vapor pressure is an equilibrium constant. If you have some idea of chemical equilibrium, then guys, let us say I represent this equilibrium. H2O liquid goes to H2O gas. And if I want to write down the Kp expression for Kp, that is the equilibrium constant for this, then that, my dear students, will be partial pressure of H2O at equilibrium. Okay, this will be the expression for Kp. This is a pure liquid. So concentration terms of pure liquids are not written. And partial pressure of H2O at equilibrium, read the definition. The partial pressure exerted by liquid vapors when there is liquid gas dynamic equilibrium. Okay. So this is nothing, guys. This Kp over here, this is nothing but your vapor pressure. This is very much your vapor pressure. So what you need to understand is that vapor pressure is an equilibrium constant. And if it is an equilibrium constant, then it has a fixed value. Fixed value. Okay. And it depends only on temperature. You can change the value of equilibrium constant only by changing the temperature. So that brings me to one of the very important properties, conclusions, whatever you want to call it, for vapor pressure. For a given liquid, okay, if my liquid is fixed, the vapor pressure, okay, for a given liquid, the vapor pressure depends only on temperature. It depends only on temperature. For a given liquid, the vapor pressure depends only on temperature. And more importantly, it is independent of, and I'll be taking lots of problems for you to understand these points. It is independent of, number one, the shape and size of vessel, the shape and size of vessel. Okay, how big or how small that vessel was, it has got nothing to do with that. Okay guys, and these are all very, very important things. Secondly, it is independent of the amount of liquid taken in the vessel. And thirdly, it is also independent of the surface area. So vapor pressure has got nothing to do with these quantities. It only depends upon temperature for a given liquid. Obviously, if you change the liquid, then different liquids will have different tendencies to evaporate. Okay. So for different liquids, vapor pressure will be different, because there we can say that for different liquids, vapor pressure will be inversely proportional to the intermolecular forces. Sir, what do you mean by this? Beta, more will be the intermolecular forces, okay, within the liquid, the higher are the intermolecular forces. So let's say we have this liquid over here. All right. So more is the intermolecular force over here, the lesser will be the tendency to evaporate. Okay. So because of that, there will be less vapor pressure. So it is inversely proportional to intermolecular forces. But for a given liquid, okay, for different liquids, it is inversely proportional to intermolecular forces. For a given liquid, students, it depends only on temperature. And as you increase the temperature, remember, the vapor pressure always increases. Now, these are the usual things, okay, which you find in most of the textbooks. Let me dig a bit deeper into this concept. So as we know that vapor pressure is the equilibrium constant. So guys, this brings me to one more very, very important property. As far as possible, the liquid tries to maintain its pressure. The liquid tries to maintain its pressure, okay, equal to the vapor pressure, Sir, what do you mean by this? Beta, if the liquid maintain its pressure equal to the vapor pressure, now you have to think of vapor pressure as a fixed constant. You have to think about vapor pressure as a constant value, which has got nothing to do with how much of liquid you are taking. Okay, what is the shape and size of the vessel? It has got nothing to do with any of these parameters. And the liquid will try to maintain the pressure of its vapors, okay, the pressure of its vapors equal to that constant value, which is the vapor pressure. Vapor pressure is a fixed constant, okay, and it is the responsibility of the liquid that it maintain the pressure of its vapors equal to the vapor pressure. And liquid can do only two things. It can either undergo evaporation or it can undergo condensation, right, students? So suppose if I have a container, all right, and in this container there was some liquid, and these were the vapors of the liquid. And let's say the pressure of the vapors, pressures of the gas, vapors, whatever you want to call them, is less than the vapor pressure. Okay, vapor pressure is scale come hai, P gas is less than the vapor pressure. So in such a scenario, what will happen? The liquid has to increase the pressure. And remember, liquid can do only two things. Either it can evaporate or it can condense. ठीक है? तो अभी उसको क्या करना है? Pressure increase करना है. So in such a scenario, there is going to be some evaporation. So here some evaporation will happen. Suppose on the other hand, I had a system in which there was liquid. These were the vapors. And my dear students, the pressure of the gas was greater than the vapor pressure. Pressure of the gas was greater than the vapor pressure. So in this case, it has to decrease the pressure. See, vapor pressure is an equilibrium constant. It is a fixed value. It has got nothing to do with anything, okay? And it can only be changed upon changing temperature for a given liquid. So if the pressure of this gas over here is greater than that fixed value, then the liquid will want to decrease it. And in that case, there will be net condensation. Here you can say net evaporation, and here you can say net condensation will happen. Net condensation will happen, okay? So liquid will want to maintain its pressure equal to the vapor pressure. as far as possible. Now, this word is also super duper important, as far as possible. So what is the meaning of this as far as possible? Let's quickly try to understand this with the help of some examples. So the first example, number one, guys, okay? So let's say that over here, we have a container, okay? And in this container, there is a freely movable piston. And this is an infinitely long container. This container is very, very long. Over here, I have taken some liquid. Let's say I have taken water, H2O liquid over here, okay? And this liquid has evaporated to maintain its pressure equal to the vapor pressure. So here you have P gas is equals to the vapor pressure, okay? And there is equilibrium within the system. Any liquid tries to maintain the equilibrium. Now, my dear students, this particular piston, which is a freely movable piston, is connected with a pulley like this, and there is a boy present over here, and what he is doing is that he is gradually pulling the piston in the upward direction. Okay, so let's quickly have a look at this example. This is a very beautiful example which will inculcate the basic meaning of vapor pressure in your minds. So gradually pulls the piston in upward direction. तो piston को वो ऊपर खींच रहा है, ठीक है? In the upward direction, gradually pulls the piston in the upward direction. All right. So this boy gradually starts pulling the piston in the upward direction, and temperature is constant. Temperature is constant. Okay, guys. And remember, I told you that this container is infinitely long. So this piston, this piston can be pulled up till any distance. Okay, so this is infinitely long. Now, what you need to do over here is that you need to plot a PV curve. Temperature is constant. You need to plot a PV graph for this process. Okay, so what is going to happen, guys? Let's try to visualize what's going to happen over here. So students, suppose I want to plot a PV graph over here. Let me draw my axis first. So this is P, this is V. Now, as this boy gradually starts pulling the piston in the upward direction, so what is going to happen? As the piston is pulled up, this gas over here, okay, the vapor or the gas, whatever you want to call it, this gas over here will expand. Okay, so the moment the gas undergoes expansion, we know something of the sorts of Boyle's law, which says that pressure is inversely proportional to volume. So if the volume is going to increase, then the pressure will decrease. Okay, because if you pull the piston, the gas will expand and the pressure will decrease. Vapors will expand and the pressure will decrease, right? So now students, the moment pressure becomes less than the vapor pressure, okay, vapor pressure is a fixed constant. All right. The moment the pressure of this gas becomes less than the vapor pressure, what will the liquid do? Liquid says that this cannot happen as long as I exist in this world. Okay, मेरे जीते जी ये नहीं हो सकता. You can't do that till I am alive. So the moment the pressure falls less than the vapor pressure, this liquid will evaporate and it will restore its pressure equals to the vapor pressure. So basically what is going to happen, as you keep on pulling this piston in the upward direction, okay, more and more liquid will evaporate and restore the pressure equals to the vapor pressure. So basically, guys, what will happen is that the pressure will remain constant, but the volume will keep on increasing. Okay, so volume has increased, but the pressure has remained constant. Now, up to which point can this happen? See, I told you the container is infinitely long, but I do not have infinite quantity of liquid. So as the liquid is evaporating, naturally the amount of liquid is decreasing from the bottom. Okay, so obviously after a certain time all the liquid will be consumed, and once all the liquid has been consumed, okay, then obviously there cannot be any evaporation. Like after certain time all the liquid has gone into vapor phase, and now if you further pull the piston, then my dear students, there is no liquid left to evaporate, and now naturally the pressure will decrease. So this will follow your Boyle's law graph, which is the rectangular hyperbola, because after a certain point, all the liquid has gone into the vapor phase. So now there cannot be any evaporation, and now the pressure is going to decrease. So this is how the PV curve will look like. And this particular point represents that point when all the liquid has gone into vapor phase. When all the liquid has gone into vapor phase. All the liquid has gone into vapor phase. So this is that particular point. So I hope you realize the importance of this word as far as possible. Okay. So after a certain time, when the liquid got completely consumed, then obviously it's not possible beyond that point. All right. So this is one very important example which will help you realize the difference between normal pressure and vapor pressure. Very quickly, let us move forward and let's have a look at one more example. Okay. Example number 2. Example number 2, my dear students, is that let's say that we have a container over here, and on this container, I have a freely movable piston. Within this container, I have a mixture of gases. Okay, I have a mixture of gases. And guys, let's say I have hydrogen gas. So partial pressure of hydrogen is 50 torr within this container. And there is H2O gas as well. So partial pressure of H2O gas is 20 torrs within this container. Okay, this is the initial assembly. And let's say the temperature is 25 degrees centigrade or 298 Kelvin. And guys, the vapor pressure of H2O. Achha, by the way, vapor pressure of H2O is also called as aqueous tension, just for H2O. Vapor pressure of water liquid is also known as aqueous tension. So vapor pressure of H2O, also known as aqueous tension. Okay, aqueous tension at 25 degrees centigrade has been given to me as 20 torr, right? And now the problem says, first part, that isothermally, which means keeping the temperature constant, okay, isothermally, the volume is halved. Okay, the volume is halved. Find pressure. So if I compress this piston to half the original volume, I need to find out the final pressure. Now, this is a very classical example, guys, which will help you understand the subtle difference between gas behavior and vapor behavior. See, for any substance, when you are solving the problem, and for a particular substance, if vapor pressure has been given in the problem, then for that substance, you have to assume vapor behavior. And for the substance about which there is no discussion of vapor pressure, like for H2O, I have given the vapor pressure. For hydrogen, there is no discussion of vapor pressure in the problem. So for hydrogen, I am going to assume gas behavior, and for H2O, I am going to assume vapor behavior. Now, obviously, you will be surprised at this statement. Sir, what do you mean by this? I mean, sir, let's talk in more detail, because sometime back you were using gas and vapor, I mean, interchangeably. Okay, but here I am going to emphasize upon that difference, that what is the difference between the gas and the vapor behavior. So let's try to understand this, guys. Now, the most common answer which I get to this particular problem from students is that, let's say the volume is halved. Okay, volume is halved. All right. So once the volume is halved, we all have heard of something known as the Boyle's law, pressure inversely proportional to volume. So volume is halved, so pressure will be doubled. And the most common answer which I get from kids is that, sir, now hydrogen will become 100 torr. Okay, and H2O will become hydrogen was 100. I mean, hydrogen was 50, so it will become double, that is 100. And H2O was 20, so this will become double, that is 40 torr. Okay, and therefore, sir, the total pressure should be 140 torrs. Now, guys, if this problem would have been that simple, then obviously I would not have wasted so much of my time to make a video on this. Okay, so this would have been a very basic level problem based upon Boyle's law. So obviously there is more to this. Now, guys, what you need to realize over here is that for hydrogen, about which vapor pressure is not given. So there is no limitation of pressure. I mean, it can have any value of pressure. Hydrogen can have any value of pressure. The more you compress it, the higher will be its pressure. So if you halve the volume, it will become double. If you 1/3 the volume, it will become triple. So for hydrogen, there is no limitation. And this behavior I am associating, I am calling as gas behavior. Okay. So for hydrogen, there is no problem whatsoever. But for H2O gas, guys, there is a problem. And for H2O gas, its pressure cannot be greater than the vapor pressure. It cannot be greater than the vapor pressure, because if P gas is greater than vapor pressure, then this leads to condensation. Okay, this leads to condensation. The pressure of H2O cannot be more than its vapor pressure. This will bring about condensation. So as you start keep moving the piston, okay, let's say we were in this position. So as you start moving the piston in the downward direction over here, then what is going to happen? Hydrogen is going to get compressed. The pressure will keep on rising. But the moment H2O is compressed and its pressure goes above 20, beyond 20, then immediately it will condense and form the liquid. Okay. And it will restore its pressure equals to the vapor pressure, which happens to be 20 torr. Vapor pressure, which happens to be 20 torr. So the pressure of H2O, students, in no situation can it go above 20, because if P gas is greater than vapor pressure, then there will be condensation. So basically what is going to happen over here is that as you compress the piston, hydrogen will keep on increasing its pressure, but the H2O will condense to form some liquid. You will notice H2O liquid at the bottom. This will be very much visible, and it will restore its pressure equals to the 20 torr value. That is the cutoff value. It cannot go above that point. It cannot go above that point. And this is what I mean by vapor behavior. For hydrogen, there is no such limitation. And that is what I mean by gas behavior. So I hope this explains the difference between these two things to you. And therefore, my dear students, the P total should be equals to 100 plus 20, which will come out to be 120 torr. Total pressure will be equals to 120 torr. Now, I have another twist for you. This was part number 1 of the problem. Now, guys, let me take you to part number 2 of this problem. And this part number 2 is that isothermally, which means temperature constant, the volume is now doubled. So instead of compressing it, I am now expanding it. The volume is doubled. Okay, volume is doubled. Okay. So if the volume is doubled, then what is going to happen? Let's say we have doubled the volume now. So this was my initial container and I have doubled the volume. So guys, if I have doubled the volume, then what is going to happen? The pressure is going to become half. So hydrogen was initially at a pressure of, okay, and I'm doubling from this initial point. All right. So hydrogen was initially at 50 and now obviously it will be half. So this will come out to be pressure of hydrogen will now become 25 torrs. Pressure of hydrogen will become 25 torrs. And sir, H2O will also be doubled in volume. So its pressure will also become half. So pressure of H2O was initially 20 and now it will become 10 torr. And now the most common answer I get for this problem, which I'm sure lots of you would be thinking as well. Sir, now this has become P less than the vapor pressure. Okay, beta, this is fine. P gas less than the vapor pressure. H2O is at 10 torr and vapor pressure is 20. So, sir, P gas less than vapor pressure, then it will evaporate and restore its pressure. Restore its pressure equals to 20 torr. Restore its pressure equals to 20 torr. And that is how the total pressure should now become, which I'm sure lots of you must be thinking. The total pressure should now become 25 for hydrogen and 20 for H2O, which will come out to be, which will come out to be 20 plus 25, which will be 45 torr, which, my dear students, is absolutely wrong. This is wrong answer. Okay. Now, what is wrong with this? Let's try to understand. See, P gas is less than vapor pressure. P gas is less than vapor pressure, which is 20. This is correct. Sir, if P gas is less than vapor pressure, evaporation should happen. This is also correct. But guys, for that evaporation to happen, liquid should be present. Okay. I hope you realize the importance of this word now. As far as possible. As far as possible. Okay. So for that evaporation to happen, liquid should be present. But did I tell you in the initial condition, by initially I told you that there is H2 gas, there is H2O gas. So where is liquid water in this container? Where do you have liquid water? Okay, there is no liquid water in the container. So if there is no liquid water in the container, then what is going to evaporate? There will be no evaporation, guys. Okay, by for evaporation to happen, pani hona chahiye wahan pe. There should be liquid water present over there. Then only evaporation is possible. So I hope you understand this now, that this H2O will remain at 10 torr only. It wants the pressure to be 20, but for that evaporation needs to happen, and for evaporation to happen, there should be liquid water in the container. So therefore, my dear students, the P total in this case will be 25 plus 10, which will be 35 torrs only, Okay, guys. So this was a very, very crucial problem. And I hope you realize now that what is the difference between gas and vapor behavior. Very quickly, guys, I'll be doing one more problem for you. And this is from, this is a PYQ from Jee Advanced. Okay. So let's quickly have a look at this problem, a lovely problem. Let me just bring the problem straight in front of you. All right, students. So let's have a look at this classical problem, which is from Jee Advanced. Okay. And you can see Jee 2011, it was for 4 marks. Let's have a look at this problem. And this is going to be your last problem on vapor pressure. To an evacuated vessel with movable piston under external pressure of 1 atm, 0.1 mole of helium and 1 mole of an unknown compound whose vapor pressure is 0.68 at 0 degrees centigrade are introduced. Okay. So what are they saying in the problem? So basically they are saying that we have an evacuated vessel which was empty initially, and it had a freely movable piston. The external pressure is 1 atm as has been given in the problem. And within this system, I am introducing, okay, 0.1 mole of helium and 1 mole of an unknown compound. Let me call it A. Okay, so 0.1 mole of helium and 1 mole of an unknown compound. Let me call it A. And for this unknown compound, the vapor pressure is 0.68 at 0 degrees centigrade are introduced. Considering ideal gas behavior, what will be the total volume of gases at 0 degrees centigrade? So this is a very, very classical problem. And remember, the piston is movable. So it can only be at rest. It can only be at rest if the external pressure and the pressure of these gases are equal. Okay. Now let us say these substances are introduced initially in the gaseous phase. Okay. These substances are introduced initially in the gaseous phase. Now, most of the students, they do get right answer to this problem, but very few of the people actually understand what's going on over here. So let me present that very, very detailed analysis of this problem for you so that you are crystal clear as far as the concept of vapor pressure is concerned. So guys, I have introduced 0.1 mole of helium and 1 mole of another compound into this container, and external pressure is 1 atm. Now, initially, both of them are in the gas phase. Okay, let's say both of them are in the gas phase. All right. So if both of them are in the gas phase, then guys, if I calculate the mole fraction of helium, that will come out to be 0.1 upon the total moles of helium upon total, which is 1.1. And mole fraction of that component A will be equals to 1 upon 1.1, which is 10 upon 11. Okay. Now, I begin to investigate if this entire mixture was in gas phase. If this entire mixture was in gas phase, then the mole fraction of helium should have been 1 by 11 and the mole fraction of the unknown substance should have been 10 by 11 if this entire mixture would have been in the gas phase. And now I begin to investigate, is that even possible for them to stay in the gas phase? Is it possible for them to stay like this? See, if the piston has to be in equilibrium, then the pressure from inside should also be equals to 1 atm, because this is a freely movable piston. So if external pressure is 1 atm, then the pressure of the gases should also be 1 atm. Then only the piston can stay in rest, right? So now, my dear students, the pressure of the gas should be 1 atm. Now, if this were the case, then using Dalton's law, what will be the partial pressure of helium? partial pressure of helium would be 1 by 11 into 1. Okay, the internal pressure is also 1 atm, and the partial pressure of A would be equals to 10 by 11 into 1. 10 by 11 into 1, and 10 by 11 into 1, guys, will be 0.9 something. 0.9 something. So if this entire mixture were to stay in the gaseous phase, then A would have to apply a pressure somewhere in the range of 0.9 something, which is greater than the vapor pressure of A. Okay, which is greater than the vapor pressure of A, which is 0.68. So you can clearly see that this P gas is greater than vapor pressure. So now what is going to happen, guys? They cannot stay like this. Okay, they cannot stay completely in the gaseous form. So basically now there will be some condensation. This A is going to move into liquid. Okay, there will be some condensation, and eventually in the final situation, my dear students, we will get a situation like this, when there will be some liquid A formed at the bottom, and over here you will be having a mixture of gases. Over here you will be having a mixture of gases, helium. Remember, the condensation has been brought about in A, not in helium. So here you will be having helium and A, and A will restore its pressure equal to the vapor pressure. So guys, the pressure A would be applying. Now don't mix this condition with this condition. This was initial condition. It could not have stayed like this. So A has now condensed to form a liquid. And now, my dear students, the pressure of A over here now in this new situation should be equals to the vapor pressure, which will be equals to 0.68 atm. It will be equals to 0.68 atm, right? And the pressure of helium, see, if it has to stay in equilibrium, then if external pressure is 1 atm, the internal pressure should also be 1 atm. So if pressure of A is 0.68, then obviously I know that pressure of A plus pressure of helium should be equals to 1 atm, and A can only apply 0.68. So obviously the rest of the pressure should be coming from helium, which should be 0.32 atms, 0.32 atms, right? And now, if you have read the problem, we need to find out the volume of the gases. Okay? So how do we find out the volume of the gases? See, you need to be very, very sure that we need to apply PV equal to nRT over here. But on which substance are we going to apply the PV and RT? See, PV and RT mein N is the moles of gas. N is the moles of gas. All right. So if I were to talk about A, okay, if I were to talk about A, guys, then do I know the, if I were to talk about A over here, let's have a look at this. If I were to talk about A, then do I know the pressure of A? Sorry, do I know the moles of A in the gas phase? I have to apply PV equal to nRT, and I have to calculate the volume. So for PV equal to nRT, N should be the moles of gas. All right. So if I have to apply PV equal to nRT on A, all right, then do I know the moles of A in gas phase? No, because some amount of A has condensed. All right. So I will be applying PV equal to nRT on helium, exclusively on helium. Apply PV equal to nRT exclusively on helium because helium has not condensed. So I am going to apply PV equal to nRT on helium, guys. So pressure of helium, why did I apply it on helium? Because I don't know the moles of A which is in the gas phase. A has condensed to form a liquid, bachcho. Okay. So PV equal to nRT on helium, what will be pressure? Pressure will be 0.32. Volume you need to find out. Number of moles of helium will remain the same because helium is not undergoing condensation. So moles of helium, you can have a look. This is 0.1 mole. Okay. So number of moles of helium will be 0.1. R is 0.0821 and temperature is 0 degrees centigrade given in the problem. So this is 273 Kelvin. And now if you solve this, guys, you will get your answer approximately as 7 liter. Okay. One more additional part of the problem can be that, although not asked in JEE, that how many moles of A has condensed. So once you have got the volume, you can now apply PV equal to nRT on A. Apply PV equal to nRT on A. So pressure is 0.68, volume is 7, number of moles is N, R is 0.082, and temperature is 273. And from this, you can get the moles of A in gas phase. Moles of A in gas phase. And the initial moles of A were how much? They were 1. Initial moles of A which were added, they were 1. And you got your moles of A in the gas phase. So now what you can do is that you can subtract these two quantities and calculate the moles of A which has converted into liquid. I mean, mole of A in liquid. Mole of A in liquid will be equals to 1 minus whatever the value of N which you get from this equation. So that is it, guys. And vapor pressure, I hope now you are very, very absolutely crystal clear, especially after these three examples, that what exactly vapor pressure represents and what is its significance and what is its meaning. It is different from the normal pressure of a gas in the sense that it is an equilibrium constant. And yes, the super duper important statement, as far as possible, the liquid tries to maintain its pressure equal to the vapor pressure as far as possible. So that's it for today. Thank you so much, students. I'll see you again next time in some other video. If you have liked the content, please do not forget to like and subscribe. Thank you so much. I'll see you soon. Till then, bye-bye, everyone. Take care and stay safe. Thank you so much.